In previous episode, we have seen that what is the race condition in Java and what kind of problem it creates. So for example, in this case, we have one field, one shared field, private static counter, so which is accessed by two threads. So what we do is we are creating two tasks, and for each for what we do in the task, right? So we are incrementing, in each task we are incrementing the counter 40,000 times. So we are creating one thread and we are passing the task, and we are creating another thread, and here we also passing the same tasks. And in the previous episode, right, we have seen that if we are incrementing that here, if our counter is here, then in that case, what will happen is we will have a race condition, and this result is unpredictable. So let's run it and see that one more time. So our expectation is that this value will be 80,000 because the thread 1 increments it 40,000 times, and the thread 2 increments it 40,000 times. We expect that this value will be 80,000, but in our case it's 44,706, and every time when we run it, the result is different, and we're getting unexpected result because of the race condition which I have explained in the previous episode. So one of the way how we can solve this problem, we are adding a synchronized block, right? Or we are adding synchronized keyword to our method. So what happens is, if we will run this method again, if we will run our main method, always we will get the result as the 80,000. So what happens is, we have moved this increment part, right? This increment part of the task, we have moved that to the separate method, and we marked it with the synchronized keyword. What this synchronized keyword makes sure says, synchronized keyword makes sure that each thread, so let's say we have in this case two threads, right? We may have more, 5, 6 or whatever. So this method is only accessed by one. It only accessed by one thread at the time. So let's say that if thread 1 accesses the increment, then in that case thread 2 cannot access it. Thread 2 should wait until the thread 1 finishes its work, and then after that thread 2 can access the increment method, and vice versa. So doing that, we make sure that we exactly increment that 80,000 times, and our result is always predictable. What's the downside of it? The biggest downside is always slow, because one thread is waiting for another thread to finish. Actually, it's the same as if we will run in this specific case, if we will run incremented 80,000 times instead of separating that work to two threads. That's how it happens. But let's also take a look how it exactly happens under the hood, right? So what happens under the hood? Under the hood, what happens is JVM creates a class so-called the monitor, which has the key to that block or to that method which is synchronized. So what that monitor has? The monitor has the conceptual, right? It's not exactly pseudocode wise. It has three fields. This first one is the owner thread. It's basically the thread that is currently accessing that synchronized block or method. Another one is the entry queue, is the which method, which thread is the next in the queue that will access that part of the code, right? We are adding that to the entry queue, and also the threads that are in the wait list, so that called the wait method. So we are adding them to the wait set. So what happens? Let's go step by step, right? So in the first step, let's say that we have started thread 1 and thread 2. So what happens is thread 1, let's say that got the key, and the thread 1 is the owner of that thread. So in that case, T2 also wants to access that. T1, the monitor is owned, the owner of the owner thread is the T1, and the T2 also wants to access that method, right? So what happens is that the T2 cannot access that, because that already, the monitor can have only, key can be owned only by one thread at the time, right? So only by one thread at the time. So what happens is JVM adds the T2 to the queue, right? Because it will be next one in the queue that will run that method. So it adds that it calls the monitor entry queue and adds that thread T2 to the queue. So what's the next one? The next one is that the JVM calls because whenever we are in the multi-threading, right, JVM works very closely with the operating system threads. So it's calling the operating system functions. So in this case, right, let's say that we are using Linux, and then the Linux, what happens is JVM calls the futex wait method of the Linux. So, and the operating system puts the T2 to the block state. So operating system blocks the T2 because T2 cannot run right now. And if let's say that there is a core that is assigned to the T2, it's freed by the OS scheduler. So OS scheduler frees that core. Let's say we have only two cores, right? Core 1 and the core 2. And the T2 is running on the core 2. Operating system frees that core because because T2 is in the block state, right? So and the next one is, let's say that the T1 finished its work and the T1 releases the monitor or releases the key to that method. In that case, JVM picks the T2 from the queue and the JVM calls the futex wait operation of the Linux. And then only after that, operating system marks T2 as a runnable, and the OS scheduler eventually schedules T2 to run on one of the CPU cores that are available. So that's exactly what happens when we are using the synchronized keyword, right? So when we are why it's important to know that, because when we are, especially in the multi-threading Java, right, we need to know that how exactly JVM works with the operating system, because how operating system scheduler schedule to run those threads on the cores. We need to know those in details, otherwise we may get some unexpected results.